All right, this is for lesson 1.7, inverse functions. Some prerequisites. You had to remember the definition of one-to-one. You have to know the definition of a function. Because a function can be a graph, or an equation can be a function, but yet not be one-to-one. And so there's two different tests. This one, function, is just basically we use the vertical line test. In other words, uh, no repeated x's. What that means is there's no values in the domain that are repeated. One-to-one, we use the horizontal line test. Line test. That means no repeated y values. That means the range is never repeated. So look at this slide. One-to-one functions. We're looking at the picture of a quadratic, the parent function, the one that's in the toolkit. And if you look at the dotted red line, it only crosses the x value one time. There's only one x value there. Everywhere you cross, there's only one. But if we look at the horizontal line test, it crossed this y value, whatever y value this is, has two different x's. There's two different places. So a parabola is a function, but it's not one-to-one. So x squared is not one-to-one because 2 to the second, which is 4, negative 2 to the second also is 4. So you have the same y value with two different x values. Functions are functions whose inverses are also functions. That's what one-to-one means. Functions are function their inverses are also functions. So I guess we're getting a hint right now that the inverse of the parabola is not a function. And that's because it failed the horizontal line test. We're going to talk in a minute about how we check if a function algebraically, what is inverse supposed to look like. So we're going to do it right now. For a function that does not pass the horizontal line test, we can restrict the domain, because what's going to happen is if we had the full quadratic, the actual inverse, and I'll show you how we come to that conclusion, it goes through the y equals x line. So a mirror image off of this would give you a picture that looked like, let's see if I can replicate it. If I replicate the blue, it's going to come down here. That part looked okay by itself. If I replicate the green, well, that would go like that. So you see what happens here. There's my new picture. That's a replica of the parabola crossing the y equals x line. The problem is it's not a function. This inverse crosses the the x value twice. Fails the vertical line test. So we knew right away that y equals x squared did pass the did not pass the horizontal line, but did pass the vertical because it was a function. But if we fix this up by restricting the domain, forget all that, take off the half of that parabola and say, I'm only going to do the green part. Because when that reflects over, well, that black is considered the inverse now. And no matter where I cross just that one, it passes the vertical line test. Because the mirror image of the green is fine all by itself. So we're saying we will restrict the domain to be all values that are greater than or equal to 0. And that's what we write here. If we restrict the domain, I can create the inverse, at least a piece of that parabola that can be used as an inverse. So I got an example here. Here is the picture of x minus 2 all being squared. And obviously, if I was to look at the line, that y equals x line, and I reflect every piece that we see over that line, I'm trying to reflect as much of it as I can, you're still getting this sideways parabola going this way. It's not going to pass the vertical line test. The new picture will not. Even if I try to make it as pretty, it's not going to pass. Nothing that is opening straight up. See, here's this absolute value. If I try crossing it over this dotted line, y equals x, I'm going to get this green piece here. I'll reflect it over here. There it goes. Well, oh, that's not green, though. I want to make it green. That reflects over here. The red reflecting over it will be over here. So here you get the same picture, but it's turned again. So as you can see, that absolute value, the new inverse, does not pass the vertical line test, just like that parabola didn't. So the secret again is, if you kind of have an idea what that inverse was going to look like, but it's not a function though. The inverse is supposed to be a function, so we say it doesn't have an inverse. But we can draw what the picture would be. And so if I just take the right side of this piece, and try to replicate that crossing over by itself, the y equals to x. And so ignore the blue for a minute. Let me graph what that reflection would be. So I'm only going to be looking at this piece here. You see, the black piece. By itself, that black piece is a function. So if I just look at the green piece here and say I'm going to restrict to only using this piece here, but when I reflect that piece over, y equals x, just a reflected image of just that leg of that absolute value, perfect. I mean, I can draw a vertical line anywhere, and it only crosses this piece here only crosses it one time. So what do we say? I want all the x's that are bigger than or equal to 2. Why? Because that's where the blue thing started. Greater than or equal to 2. That I can restrict the original picture to just that piece. The absolute value, I want x to be greater than or equal to wherever this vertex was. That's a -2. So greater than or equal to a negative 2 will work just fine. Now, the tricky part here, trying to verify, prove that a function and another function are inverse of each other. So here's this fancy definition. F of x and g of x are inverses. If and only if. That means it has to go both ways. That f of g of x has to be equal to x if you do all the work and simplify it. But at the same time, g of f of x also has to be that function. So let's try it here. F of g of x, f of g of x means all of the g, remember this, all of the g has to be plugged into the x of f. So what does that look like? Well, that looks like the 3 minus a 4 times all of that. So I'm going to go 3 minus x divided by 4. So when I see a 4 in front of this fraction here, the denominator here will cancel. That turns into 3 minus, I still have a 3 right here, so I'm distributing that minus. Then I have a minus being distributed, see it went to here, to the minus x. That becomes minus plus x. 3 minus 3 plus x is x. Okay, good. That's the one side. But now I also have to check g, and I'm going to write it different just to remind you that I don't have to use the fog or the golf. I can go g of f of x. It means the same thing as golf. In this case, in that case, all of the f has to be plugged into the g. So 3 minus 4x has to go in place of that x right here. So that looks like this. 3 minus x. X will be 3 minus 4x in parentheses. 3 minus 4x in parentheses. Still all divided by 4. At least that part. 3 minus divided by 4. Well, let's try to simplify that. Again, I'm going to have to distribute this minus twice. 3 minus 3 plus 4x, all divided by 4. 3 minus 3 cancels out. 4x divided by 4, the 4 equals to x. So yes, they are inverse of each other. That's how you do it. Let's check to see if we're right. Oops. Yep. Let's do another one. Let's verify. Usually if they say verify, it probably is true. But if they ask you, are they inverse of each other, that's different. Oops. Sorry about that. So let's check f of g of x. All of g gets plugged into the, all of g of x gets plugged into the f. So all of this has to go in here. So here goes, equals to 1 minus all of that. That's the cube root of 1 minus x. So 1 minus, and I did, let me back up here. Let me make sure I didn't cover, oh, I did. I covered up the cube. So that's important. It goes into this x right here, but there's still a cube. So all of this x got cubed. Okay, so here's what's happening. If you have a cube root and you cube it, it actually cancels each other out. Square cancels out square root. Cube cancels out cube root cancels out cube. So that turns into 1 minus, all I have left now is the insides, 1 minus x in parentheses. Distribute the minus. That's 1 minus 1 plus x. 1 minus 1 does cancel out, leaving x. Now let's try and do g of f of x. So that tells me all of f, and I'm going to erase my scratch work up here so I can see it. All of f, all of 1 minus x cubed, has to be plugged into only the x that is here. So that's still going to give me the cube root symbol, cube root of the 1 minus 1, minus the, let's see, 1 minus x cubed, 1 minus x cubed, and I got to put that in parentheses. So the 1 minus x cubed becomes the x. So there's a minus out front here. Let me handle what's inside this first. Let me distribute this minus. That turns into cube root of a 1 minus 1, because 1 negative in front of a 1 is minus 1. Negative in front of a negative x cubed becomes a plus x cubed. 1 minus 1 just cancels, leaving the cube root of x cubed. And like I said before, cube root cancels out cube, leaving x. So true, they are inverse of each other, are inverse of each other. Let's see if the author agrees with me. Yeah, looks very similar to what I did. Just real clean because it's all typed, and you don't have to worry about any nasty handwriting. All right, inverse functions where the domain and range are interchanged. So how do you find the inverse of a function? It's very, very simple steps. First of all, state what the domain and range is of your original function. It always helps to know what the domain and range is. That was like lesson 2 of chapter 1. Then, because you're looking at a function, y equals something, most likely. But whatever it is, switch the x and the y around. Now solve it for a y. And then replace the y, the new y, because you're switching around and you're solving for y, replace it with the term f inverse of x, which means the inverse of the function. Because when you resolve it for y, it's a new function. The new y really is f of x inverse, with a little 1 up there. That's what that means. It looks like a negative 1 power. So state the domain and range. In this case, are we dealing with okay, we are f of x is 2x plus 5. It's just a line. It's just a line. So we know all lines, the domain is all real numbers, and the range is all real numbers. So I take this function, this is my y, equals to 2x plus 5. Switch the x and the y around. X is 2y plus 5. That's what this is. And then what we do is we solve it for this y. This y here actually is not the same as that y anymore. So it's very simple to solve this for y. Just get rid of the 5 by minusing 5, then get rid of the 2 by dividing. And we'll look at the right side in a second and probably verify that that's exactly what we do. So I take the 5 and move it over. X minus 5 divide by the 2 is the y, but that becomes f inverse of x. So x minus 5 over 2, is that what they have? X minus 5 over 2. And there is another way of rewriting it. You could treat it as two fractions. You could also say x can be divided by 2 minus 5 divided by 2. Okay, so this problem looks a little harder, but it's all worked out for you. We start out with what our domain are for a rational function, and you know the denominator cannot be a 0. So that's the easy part. I admit finding out that x cannot be a 2 because 2 minus 2 would give you a 0 in the bottom. You can't divide by a 0. Now, the range is a little trickier, and we'll talk about another time, but there's a way to find out why you're going to find out why the y value cannot equal to a 1. It won't be clear just yet, but at the end of the problem, it's a lot easier to see it. But there they go again. There's my y. They changed this to y. Here it is. And what we want to do is switch the x and y's around. Now, they did some work first. I'm trying to see if they did what I'd be thinking. They tried getting the denominator. They did switch the x and the y's. I do see that. I don't. It's in this black part right here. Let me try to highlight it. It's right in here. See, instead of y, they wrote x. Instead of an x and an x, they wrote y over y. That's their first step. It's in black. Then they got rid of the denominator, y minus 2, so that cancels out, but I have to multiply that by y minus 2. Then it means they distributed the x, so there you got your xy or yx, doesn't matter, minus 2x. Now we have the y plus 1 by itself. There you go. And the whole goal is to solve for y. So unfortunately, let me get a little bigger here. They add 2 x's to both sides, and then they're going to be getting rid of the y. So then they ended up coming up with a new line here. xy minus y equals 2x plus 1. Factor out the y. Bingo. That's what I needed. Because then I can, when I factored out the y of an x minus a 1, that cancels out if I divide both sides by x minus 1. And that's what they did. See, they divided that by x minus 1. That one doesn't cancel, though. So there's your new function. Y equals 2x plus 1 over x minus 1. I can do that from scratch if somebody wants me to do it from scratch and give you all the details. But it's already done for you because now that you've seen how to do it, you need to practice those steps. Change the x and y around, solve for y. That's the hardest part, solving for y. But look at the answer here. Look at the denominator, x minus 1. The reason the range up here could not be a 1 is because that becomes a domain. See, it becomes the domain that we know the bottom now, that x cannot be a 1, which used to be called the y, if you think about it. Because the x and y switch. The domain becomes a range, the range becomes a domain. So you have to think about, and it's easier to see it at the end, I admit it. Okay. Domain and range of the inverse. Let's see if they're playing fair. These are the same two problems we've got done doing. We had a line, and we still have a line. That was that first one we did. So the domain and range didn't change at all. We had a regular function, a rational function, and we said the domain cannot be a 2 ever, and we said the range will not be equal to a 1. And what happens is when the domain becomes a range, in our new problem, the domain cannot be equal to 1, and the range cannot be equal to 2 because they switch places. The domain and range always switches. If you know clearly what's happening with this original function, sometimes it's just good to look at a graph and see. We did that before when we did our domain and range problems. Look at the graph and see what can x's not ever be. Look for that vertical asymptote. Look for the horizontal asymptote to find out what the y cannot be. Sometimes it's easier to do that way. And I believe that's the last problem on this demonstration. So do the videos that I've posted for you, including this one. Take your notes. And make sure you do your 1.7 mom assignment.